Hi everyone, my name is Han Seok-son. I'm an associate professor at the Department of Industrial Engineering, and I'm going to be your lecturer instructor for IE 515 course, which is, what is that? Stochastic Process Modeling course, okay? This is my very first time to teach this class. So I believe I'm going to also learn something while I'm teaching this class with you for the rest of this semester. So like I said, we are going to learn about the stochastic process, okay, something for the rest of this semester. And I believe this course would be introductory level of graduate course. And also one thing I'd like to tell you is rather than focusing on the probability theories, most of the time we are going to talk about how to model. So how to solve the real world problem, okay? Most of the time I will try to give you very simple, easy example problems. Sometimes we're gonna invest some little bit longer time to solve certain real world problems, okay? I'm not going to go over our course syllabus. Earlier today, I've released our Canvas website, so please go visit and then try to go through all the details about it, and then let me know if you have any questions, okay? So this course is basically about the introduction to the use of stochastic process in the real world system. And the prerequisite is that to engineering data analysis and ordinary differential equations, but I believe I'm going to try to cover every single topics from the very basic, so most of you will be okay, as a graduate student standing. I've listed my office hour and reference materials and course objective and many other contents related to our class. So please take some time to read through, okay? Okay, so okay, so what is stochastic process? Do you have any idea? Have you heard about stochastic process? Okay. There is nothing but a collection of random variables. Okay? So stochastic process, x of t, is a collection of random variables. You know, the random variable is a set of possible values from a random experiment. Is that right? So for each t, let's say x of t or x of t is a random variable. And the index t here is often interpreted as time. So as a result, we refer to x of t as the state of the process at certain time t. Okay? So for example, x of t might be the total number of customers that have entered a certain bank by, let's say, 10 o'clock in the morning. Or the number of people in the grocery market at noon, certain day of the week, and so on, okay? And the set T, the capital T, is called the index set of the process, okay? So when the capital T is a countable set, the stochastic process is said to be a discrete time process. Of course, if T is an interval of the real time, then we call it continuous time process. Is that right? Okay. So, this is my very first time to use this smart board. So Let's see how it's going to work. So let's say x sub t t equals 0, 1, 2, and so on. Can you see this clear? Okay. Okay. So this is the discrete time stochastic process, right? Indexed by non-negative integers, 0, 1, 2, and so on. Is that right? Whereas, let's say x sub t, and then t is greater than equal to 0. Let's say. Then this is the continuous time stochastic process indexed by non-negative real numbers. Is that right? Okay. And what I've heard is on your current screen, the resolution is not that great, but I believe on your recording, which will be reserved in the distance education server, will be a lot better than the current screen. So that's a good thing. Okay. Okay, I need to press this. Okay. So these are the common stochastic processes. Okay. So the stochastic processes include discrete time Markov chain, continuous time Markov chain, Bernoulli process, Poisson process, and birthdays process. And we're going to explore all of this later in this course. Okay? Okay, and all of these four distributions belongs to the Bernoulli process. And today we are going to talk about Bernoulli process. Okay? So let's suppose there is an experiment whose outcomes can be classified as either a success or a failure. Okay? So flipping a coin is a good example for this experiment. Okay? So whenever you flip a coin, you always have head and tail, right? So this is a good example of the Bernoulli process. Is that right? So if we set, let's say, x equals 1, if the outcome is a success, and 0 if it is a failure, so let's say, let me write it down. It's about the same, but let's say x equals 1 if success, and 0 otherwise. Otherwise means is failure, right? Then this random variable x has a Bernoulli distribution with parameter p. Okay? So what is parameter p? That is the probability of being a success. And the probability mass function of x is given by this, right? Px equals 1 equals p, and px equals 0 would be 1 minus p, or sometimes we call it q. And the p is again, the probability that the outcome is a success. Okay? Just keep in mind that. So we just talked about Bernoulli random variable. Okay? That is a single experiment whose outcome can be classified as either a success or failure. Okay? And the mean value of the Bernoulli random variable would be just p. And the variance would be 1 minus p times p. Okay? So we are engineer. So we just use those formula. But of course, it's better for you to understand how we drive those formula. But we know that scientists, mathematicians, they already proved this. So we're going to use this for us to solve real-world problems. Okay? Okay. Now let's talk about Bernoulli process. Okay? the stochastic process x of n is a Bernoulli process if each random variable is statistically independent of each other and each random variable has Bernoulli distribution with parameter p. Okay? That is very important, very fundamental. So we've known that the random variable x has Bernoulli distribution with parameter p if the outcome of an experiment can be classified as either a success or a failure. Is that right? So let's take an example for the Bernoulli process. First, at a certain intersection of two streets, let's say about 30% of the vehicles turn left. So in this case, if we define x of n equals 1, if the nth vehicle turns left and 0 otherwise. Okay? Then x of n follows Bernoulli process with parameter p. P equals 0.3. Is that correct? Okay? You remember the Bernoulli process x of n, the stochastic process x of n is a Bernoulli process if the two conditions are satisfied. What are those conditions? Each random variable is independent of each other, and each random variable follows Bernoulli distribution with parameter p. Okay? If those two conditions are satisfied, then the stochastic process x of n is a Bernoulli process. Okay? So obviously, the first example is a good example of the Bernoulli process. Is that right? Because in general, each car at the intersection make its own decision, right? To make a left turn or not, right? And each car at the intersection can make a left turn. Like I said, each driver at the intersection can make their own decision. So each car's decision is independent, right? Each other. And another example, like I said earlier, flipping a coin would be good example of a Bernoulli process, Bernoulli trial. And also rolling a dice could be Bernoulli process if we assume that, for example, a success is occurred whenever you have 6. Okay? Unless otherwise, let's say you're going to have failure. Then this is another good example for the Bernoulli process. Okay? Just keep in mind that outcome of the Bernoulli experiment can be always classified as either a success or a failure. Okay? Any questions so far? Okay. So I said flipping a coin would be a good example of a Bernoulli trial. So let's reconsider a single experiment or trial of flipping a coin. So if we make this experiment independently, let's say n different times, okay? Then each of them result in a success with probability p and a failure with probability 1 minus p. So this is a Bernoulli process. Is that correct? Right? Now, if n sub n is said to be a number of successes that occur in those n different trials, then n sub n is said to be a binomial random variable with parameter. This time we have two parameters, n and p. N is the total number of trial, and p is being a success, probability of being a success. Okay? So basically, binomial distribution describes the random number of successes in a fixed number of trials. Just keep in mind that. Okay? And the probability mass function of binomial random variable has two parameters, like I said, which are n and p. So in summary, suppose that there is a probability of being a success, which is p, on any single trial, if we make this single trial n times independently, then the binomial random variable counts the total number of successes in these n different trials. Okay? And the mean value of the binomial distribution is n times p, and variance is npq, or n times p times 1 minus p. Okay? Okay, unlike other distribution functions, I would say the binomial distribution doesn't have any special pattern. Okay? So for the next couple of slides, I'm going to show that. So the first graph, this graph has been obtained from binomial distribution with parameters n equals 4 and p equals 0.1. Okay? So how does it look like? It looks like maybe exponential distribution, right? Something similar. How about this? This graph has been obtained from another binomial distribution with different parameter values. This time, n equals 4, p equals 0.5. So it looks like triangular distribution, right? How about this? It's from binomial distribution with n equals 10, p equals 0.2. So it looks like, I say, beta or Weibull distribution, something like that. Okay? How about this? It looks like a normal distribution, right? Bell shape, right? But it's from another binomial distribution with different parameter value. P equals 0.5 and n equals 10. So we may say that binomial distribution doesn't have any special pattern for sure, right? Okay, so now let's take an example. Let's say a left-turn lane at a certain intersection has a capacity of only 3 cars, okay? And 30% of vehicles arriving at the intersection, they wish to turn left. Now, if 6 vehicles arrive during a red light, then what is the probability that the capacity of the left-turn lane will be insufficient? How to solve this problem? How? So the first, you need to collect some required information. So by reading through this problem description, what information did you collect? Total number of trial, total number of cars. What is that? 6 vehicles, right? Because it does say if 6 autos arrive during a red light. So that means total number of vehicles arriving at the intersection during the red light is 6. So we're going to say n is 6. Then what about the probability? P is 30%, it does say, right? So I'd say n equals 6 and p equals 0.3. And if you say x is equal to number of autos that wish to turn left. Okay? Then how do you construct the desired probability? What do we want to know? We want to know the probability that the capacity of left turn lane will be insufficient. So using the x, how do you express the desired probability? What is that? We want to know probability. X is what? X is greater than 3. right? Because we know that the capacity of the left-turn lane is only 3 vehicles, 3 autos, right? So the desired probability has to be probability that x is greater than 3, okay? Obviously, if 4 more cars wish to turn left, then left-turn lane would be insufficient. Is that right? Does that make sense? So what is this? That's going to be probability x is, okay. X equals 4, 5, and 6. Is that right? Oh, I'm sorry. I forgot to mention this. So in this case, variable x follows which distribution? There is total number of autos that wish to turn left within 6 autos, right? You remember binomial random variable counts random number of successes within a certain number of trial, right? So that's exactly what binomial random variable counts for, right? So obviously x follows binomial distribution with parameter n equals 6 and p equals 0.3. So obviously we're going to use binomial distribution for calculating this probability. Is that right? So how'd you get it? That's going to be 6 combination 4. So 6 combination 4, or let's say I'm going to use this. It's the same, but this is the same, right? And then probability of being success, which is 0.3 to the power 4, right? And then 1 minus 0.3 times, to the power 6 minus 4, right? That's this probability, right? This first term. Second term is the same. Let's say 6 combination 5, 0.3 to the 5th power. That's going to be 0.7, which is 1 minus 0.3 to the 6 minus 5. And then the last term, this probability would be 6 combination 6, 0.3 to the power 6, 0.7, 6 minus 6. Okay? So you should be able to get this value in the end, of course. Actually, you don't need to compute because I already provide you the next screen here. So the answer is what? That's going to be the summation of these 3 bars, okay? Which comes up with 7.047%. Okay? That's going to be the answer in our example. Okay? Any questions so far? Okay, now let's talk about the times of successes. Okay? Suppose that the independent trials, each having the probability P of being a success. Again, you may want to reconsider the flipping a coin experiment. Okay? So we are considering the same experiment whose outcome is always classified either of being a success or failure. Okay? So right now, we are always considering the Bernoulli trial, Bernoulli experiment. Okay? So this independent trial is performed until a first success occurs. Okay? So if we set, let's say, okay, let me write down here. So let's say up here, t sub 1, that is the number of trial required until you get the first success, okay? Until the first success. So what is t sub 1? In other words, that is the time of first success. Is that right? Okay, so t sub 1 is the time of the first success. Then this t sub 1 is said to be a geometric random variable, okay? Geometric random variable with parameter p. Then t sub 1 follows geometric random variable with parameter p. Again, p is the probability of being a success. Okay? Then we'd like to know, probably, okay, we still consider the same example, okay, which is this example. But we'd like to know how to answer to get the probability that seventh car is the first left-turn car. We'd like to answer this question. So in that case, we can say that t sub 1 is the number of authors, right? Arrived until the first left-hand car. Okay? Does that make sense? Okay? So in that case, what is the desired probability? That's going to be probability T1 has to be equal to 7, right? Because we want to know the probability that the seventh car is the first left-hand car. Is that right? So in that case, using the same formula, 1 minus 0.3 to the 7 minus 1. Because first 6 car will not turn left. Is that right? But the 7th car will turn left. So the formula should be this, which is identical to this. Does that make sense? Because the first 6 car won't turn left, and the 7th car, so that will be the first left-turn car. Okay? Make sense? Okay. And this screen just tells you the mean value and variance for the geometric distribution. Those are 1 over p and 1 minus p over p squared. Okay? Okay. This screen just tells you that, okay, so from this graph, I just say here, the expected value is 4, okay? But you can see that the smaller values are much more likely happen, okay? Obviously. Okay, now we are going to talk about negative binomial distribution, or someone says the same terminology, Pascal distribution. Have you guys heard about this distribution? Okay. So as an extension of the geometric distribution, we could think of the time of the kth success. Here, k is greater than 1. Of course, if the k becomes 1, then we're going to go back to the geometric distribution. Okay? Anyhow, then the time of the kth success, in that case, follows negative binomial distribution or Pascal distribution. Okay? So we just let tau sub I represents the additional trials performed after I minus 1th success in order to achieve ith success. Then T sub k will have this. So T sub k has T sub k follows negative binomial distribution. Okay? So let's consider this. Because I'm going to draw a picture, so I'm going to use another program.
You can just close that right there.
Oh, just close it? Okay.
Yeah.
Oh, then this is just new screen, right?
Uh-huh.
Okay, thank you. Okay. So I'm going to draw a timeline. So let's say this is a timeline, okay? And this is, let's say, 0. Maybe, I still can use this pen,
Yeah,
right?
you can use that pen.
Oh, that's a lot
easier.
better. Okay. So let's say this is 5. Oh,
Yeah, you have to pick
okay.
the pen.
5, and then this is 10. So I have 1, 2, 3, 4, 6, 7, 8, and 9. Okay? So these are timeline, let's say. And then let's say the first success occurs at time t equals 1. Let's say second success occurred time t equals 5. So this is second success occurred. And let's say the third success occurred at time t equals 10. Then what is this? Interval. That's the 1, right? And then after that, until the next success, time interval would be 4. Okay? And then next one would be 5 for sure. Okay? So going back to the previous screen here. According to the T sub k and the definition of tau sub I, we can say that time of the third success can be represented by summation of tau sub I. I will be 1, 2, 3. Okay? So it's going to be tau sub 1 plus tau sub 2 plus tau sub 3. Tau sub 1 is 1. First interval is 1. Tau sub 2 is 4. Tau sub 3 is 5. Okay? So what is this? That's going to be 10. Okay? So time of the third success occurred at time t equals 10. Is that correct? So let's go back to our PowerPoint slide. And then let's move to the next screen. So what I can say is, these two statements is always true. Okay? So referring to our example here, we can say that here, the third, okay, I'm going to use different color. Okay. So here, the third success, how come? The third success occurred when? On trial number 10, right? If and only if there are exactly 3 minus 1, which is 2 successes occurred in the first 10 minus 1, which is 9 trial. Okay? That is true. Going back to our figure, the third success occurred on trial number 10 only if and only if there are exactly 3 minus 1, which is 2 successes occurs in the first 9 trial. Okay? So the first statement is true, right? How about the second statement here? There is a success on the 10th trial. Is that correct? So, of course, we know that the third trial occurred at the 10th, time t equals 10. Okay? So keep in mind that this statement, 2 statements are always true. Okay? Okay, now let's take another example for the negative binomial distribution or Pascal distribution. So a left turn lane at a certain intersection has a capacity of 3 vehicles, and 30% of vehicles arriving at the intersection wish to turn left. Now we want to know what is the probability distribution of the number of arrivals which cause the capacity of the left turn lane to be exceeded. So by using the negative binomial distribution, we could obtain the desired distribution. So first, if we set, let's say, t sub 4, let me use the probably red color, that'll be better. T sub 4 is the time required until the fourth left-hand car, right? Left-hand autos. So there is a time until the fourth success, okay? Because if 4 or more cars wish to turn left, it is overcapacity of the left turn lane again. Is that right? So the desired probability would be set equal to this. So if you look at this table, we would say until 30 cars arrive and at the intersection, the left turn lane is overflow with almost 99%. Okay? Does that make sense? Okay. And the result is depicted in the bar graph here, the same result. So I'd say until 30 cars arrive at the intersection, here, the left turn lane is overflow with 99%. Okay? Okay, so far we've learned about the stochastic process. And the stochastic process is a Bernoulli process if 2 conditions are met. What are those? Do you remember? The first condition is each random variable in the stochastic process are independent each other, right? And each random variable in the stochastic process follows Bernoulli distribution. Is that correct? Right? So keep in mind that. Okay? Okay. Now, let's take a break a little bit. Okay? So let's take some time to get to know each other. We have only 4 people in this room, except for me. Okay, I'd like to share these pictures that I've taken. So the first picture here is taken back in 2011. At the time, February 24th, around that time, we have a heavy snow, believe it or not, here in Las Cruces. So for 3 days, all the school has been closed. Okay, all the government buildings were also closed. And at the time, I've invested the half day to build up snowmans. It's a pretty good size. It's about, I believe, is 7 feet, little less than 7 feet. It's very, very tall. And then I took a picture with my 2 daughters there. And then back in 2015, we have another good snow. So the time I built up igloo. Kind of is a good shape, right? It's also pretty good size, about 5 feet tall. So I asked my 2 daughters in there and then took a picture of that. Is that nice? I made a heart shape, the entrance heart shape. But since then, we don't have any good amount of snow until this time. So I was not able to update another photograph here. Okay. Okay, so probably from you, why don't you tell us a little bit about yourself?
Hello, my name is India, and I'm glad to be here. I'm a graduate student, and
Are you in industrial engineering program?
Oh no, I'm from Applied Statistics, but this course sounded interesting.
Okay.
I wanted to know more about stochastic processes, so yeah, I'm glad to be here.
Okay, thank you.
Hi everyone, my name is Fawaz. I'm a grad student in IE.
Okay.
My background is industrial and manufacturing and system engineering.
Thank you.
Glad to be here.
Yeah, first year PhD student, right? Okay. Are you also in PhD program? Master's program. When are you going to finish your degree then?
Hopefully December.
December. Oh, okay. That's nice.
Hello everyone, my name is Mahmoud Elio, and I'm a graduate student in industrial engineering, and my undergrad's in industrial engineering as well,
Okay.
from Michigan State,
Mm-hmm.
and this is my last semester hopefully.
Last semester?
Yes.
Okay.
So.
Thank you. You can sit. Okay. Thank you. I'm sorry. It's fine.
So my name is Jesus. I'm doing a master's in industrial engineering. My background is mechanical and aerospace, and this is my second year. And
Second year?
yeah,
Okay.
I hopefully
So
will
you're
be.
also about to graduate?
Yeah, hopefully by the end of the summer.
Okay. Are you going to write a thesis for your degree project or degree? No?
Yeah, I don't think so.
You're going to do the course only
Yeah,
options?
I read it for something.
Okay. Thank you.
Thanks.
Okay. I'd like to have more interaction during the regular class. So not sure how I could manage that, but frequently probably we're going to have a in-class exercise session. So I'm planning to distribute the problem sets and then give you time, at least a couple of minutes, so you guys can think about how to approach to solve the problem. And then if I could, I'm going to ask if there is any volunteer, then you can come out and then share your idea. After that, probably we can discuss more in depth. Okay? Okay. Thank you. So let's go back to our lecture. Okay, now we're going to talk about another stochastic process, which is Poisson process. Okay? So all of these three distributions belongs to the Poisson process. They are Poisson distribution, exponential distribution, and Erlang distribution. Have you guys heard about all of these three? Only some of them? Exponential. Okay. Poisson as well. Okay. Okay. So here, what did I say? Okay, first terminology that I want to explain you is the counting process. Okay, and I'd say a stochastic process x of t or n sub t this time. Stochastic process is a counting process if the n sub t represents the total number of events that have occurred up to certain time t. Okay? And the counting process, n sub t, must satisfy all of these conditions. So let's take an example for these conditions. So if n sub t is the number of customers who have entered, let's say, a bank at or prior to certain time t, then n sub t is a counting process in which an event corresponds to a customer entering the bank. Okay, does that make sense? So for example, a local bank opens at noon, and let's say 10 people have entered the bank by 1 o'clock in the afternoon. And the total number of people entered into the bank by 2 o'clock in the afternoon is 15. Then here, the last condition says 15 minus 10, which is 5. 5 people have entered the bank between 1 o'clock in the afternoon and 2 o'clock in the afternoon. Does that make sense? And if n sub t is the total number of customers in the bank at time t equals t, then in this case, n sub t is not a counting process. Do you know why? I just told you, n sub t is the total number of customers in the bank at certain time t. Then, in this case, n sub t cannot be the counting process. Why is that? Because in that case, number of customers could be decreased after a certain time of period. So this violates condition number 3. Does that make sense? Okay? So there is a slight differences. Okay? How you define the variable. Okay? And one of the most important counting process is the Poisson process. Okay? Other counting process includes, let's say, the renewal process. That is the generalization of the Poisson process. But we are not going to talk about it in this class. Okay? That is a little bit advanced topic. So in this case, we are not going to talk about it. Okay? So the counting process, n sub t, is said to be a Poisson process having a certain rate, lambda. Okay? And lambda is assumed to be a non-negative value. Okay? If n sub t equals 0, which means the counting of events begins at time t equals 0. Okay? And the process has independent increments. For example, n sub t must be independent of n sub 2 minus n sub 1. Okay? That is, number of events which have occurred by time t must be independent of number of events occurring between times 1 and 2. Does that make sense? Okay? And the condition number 3 means that the process has stationary increments. That is, the distribution of the number of events which occur in any interval of time depends only on the length of the time interval. So here, the number of events in the interval t sub 1 plus s and t sub 2 plus s has the same distribution as n sub t sub 2 minus n sub t sub 1. That is the number of events in the interval t1 and t2. Is that correct? So keep in mind that Poisson process is a counting process that has two important properties, which is independent increment and what is that? Stationary increment. Okay? If the counting process satisfies those two conditions, we can say that that counting process is a Poisson process. Okay? And all three of these distributions belongs to a Poisson process. Okay? Okay, the first one, Poisson random variable. Poisson random variable is a count of the number of events that occur in a certain time interval. For example, the number of cars passing through a certain intersection in a 5-minute interval could be a Poisson random variable. Okay? And the probability mass function is like this. Okay? These are the Poisson probability mass function. And I will say there is an important property of the Poisson random variable, which is that it may be used to approximate a binomial random variable when the binomial parameter n is very large and p is very small. Okay? I'm going to show you how this is possible. Suppose n sub n is a binomial random variable with parameter n and p. Then we let v is, or nu equals np, n times p. Here the nu is the expected number of arrivals, okay, in certain time interval 0 and n, okay. Then the probability mass function of binomial random variable with parameter np would be like this, right? And for very large n and for very small p-value, this whole part becomes 1, and this numerator becomes e to the negative new's power, and this denominator becomes 1. Okay? As a result, we have come up with this. Okay? And the corresponding probability mass function would be like this. Here, the lambda is the mean rate at which the events occur. Okay? So these are exactly same as probability mass function of Poisson distribution. Okay? So we may say that the Poisson random variable can be used to approximate binomial random variable if n is very large and then p is very small. Okay? This is very useful feature, okay, in real life. So keep in mind that. I'm not sure, but you can have you can research through Google. But as I recall my memory in general, if n times p is 5 and n is 50, then we can use Poisson. You might come up with a different number here. So I want you to do some Google search on that. But and also if n times p is greater than 5, then it's safe to use binomial distribution. But let me know if these numbers are different from what you come up with. Okay? And the mean and variances for the Poisson distributions are identical, which is lambda times t. Sorry. Okay, now let's talk about exponential distribution. Okay? Suppose that the number of arrivals in an interval has the Poisson distribution with arrival rate, which is lambda per second. Then we let t sub 1 is the time of the first arrival. Then what is the distribution of t sub 1? Let me just tell you the result first. The answer is exponential distribution. Okay? So in this previous screen, I said t sub 1 is the time of the first arrival. So this probability represents the no arrival occurs until time t. Is that right? It's the same thing here. No arrival occurs until certain time t. Okay? So here, a continuous random variable t, this capital T, is said to have an exponential distribution. Okay? So T has exponential distribution with parameter lambda. Okay? And we assume that lambda is greater than 0. Okay? And is PDF probability density function is given by ft is equal to lambda times E2 minus lambda t if t is greater than or equal to 0. And 0 otherwise. T is less than 0. Okay? So, which is same as this, right? This one. Or equivalently, if is CDF, cumulative distribution function is given by capital Ft is equal to integral negative infinity to t, then f y dy is equal to 1 minus E2 minus lambda t. If t is greater than or equal to 0, same, and 0 otherwise. T is less than 0. Okay? So this is also the same as this up here, right? So we may say that t sub 1 follows the exponential distribution with parameter lambda. Okay? And the mean value for the exponential distribution is 1 over lambda. Variance is 1 over lambda square. One thing I want to stress out here is exponential distribution is very important because it holds a special property that is called memoryless property. Have you guys heard about that? Okay. So a random variable x is to be memoryless if the following condition is satisfied. So here, the condition in this equation number 1 is equivalent to the condition in equation number 2. Okay? And also condition in equation number 2 is equivalent to this equation number 3. And you know this equation number 3 is satisfied when x is exponentially distributed. Okay? So this part can be expressed as e2 minus lambda s plus t equals e2 minus lambda s times e2 minus lambda t. Okay? Because this equation number 3 is satisfied when the x is exponentially distributed like this. So we may conclude that exponentially distributed random variable has memoryless property. Okay? So keep in mind that this is very important property. So let's take an example. Suppose that the amount of time one spent in a bank is exponentially distributed with mean of 10 minutes. Okay, so from here we collect information. What is that? What is lambda? Lambda is the mean rate. It's not the mean time. So you need to take the reciprocal of 10. So that you're going to have 10 over 10, 1 over 10 per minute. Is that correct? So from this, by reading through this first sentence, you should be able to get lambda value, which is 1 over 10 per minute. Okay? Then this is the desired probability. What is the probability that a customer will spend more than 15 minutes in a bank? So if I said x represents the amount of time customer spends in a bank, then the desired probability would be x is greater than 15. Okay? Because we know that lambda is 1 over 10. The desired probability would be 0.22. Okay? Now, next, what if we modified the question just a little bit so that this time we'd like to know the probability that the customer will spend more than 15 minutes in the bank, given that he is still in the bank after 10 minutes. I'm so sorry. I'm terribly sorry. I forgot to give you the handout. I'm sorry. Every class, I'm going to try to distribute the handout. So if I don't do that, please ask me. I'm so sorry. I totally forgot to give you that. Okay. So I believe we are way back. down there. Okay? Yeah. Okay. Okay. So hopefully you guys can customize your own note, okay? Rather than sit back and doing nothing, try to make some note, okay? Sometimes I intentionally give you the incomplete lecture note so that you can fill out, okay? Whatever you want. Okay, where was I? Okay. So how do you answer this question? The desired probability would be like this. So probability that a customer who has spent 10 minutes in the bank will have to spend at least 5 more minutes.
So actually,
Yeah.
so you're going to calculate the 5 minutes.
Right. So because what? Because of memory list property, okay? I just talked about the memory list property. The exponential distribution basically does not remember that the customer has already spent 10 minutes in the bank, okay? So the desired probability would be reduced down to probability that x is greater than 5 because of memory list property, okay? Does that make sense? So we use this formula, basically, right? The first equation. We use that to answer that question. Is that right? Okay. Okay, now let's talk about time of the kth arrival. So I would say this is the extension of the exponential distribution. Exponential distribution is related to the time of the first arrival. Okay? So let's say t sub k is the time of the kth arrival. Then tau sub k, which is t sub k minus t sub k minus 1. That is the time between arrivals. Okay? K1 minus K. Then suppose that tau sub K has identical and independent exponential distributions with weight. Then T sub K is a sum of K random variables with exponential distribution. Then it is said to have a K along distribution. Okay? So today we are talking about so many different distributions. Okay, I hope you guys not confused about that. Okay. In the end, I'm going to summarize, and then I'm going to give you the summary table. Okay. Okay. So this screen shows that the probability density function and the cumulative distribution function of the K along distribution. Just to let you know that the L-long distribution is a special case of gamma distribution, okay? Where the shape parameter here, k, is an integer. So here, if the k takes an integer value, then L-long distribution becomes gamma distribution, okay? So gamma distribution, oh, did I say so? Okay. So in the in the L-long distribution, k takes the integer value. Did I say right? But for the gamma distribution, k takes the real value. That's the only difference. Sorry. Okay. And actually, the cumulative distribution function of the L-long distribution can be computed by using Poisson distribution. This is very useful feature. So you may want to keep in mind that. So this screen shows how it could be done. So here, the first probability, saying that probability that case event have occurred within time t, so that is less than equals t, okay, is equal to the probability that the number of events, n sub t is the number of events, occurred within time t is at least k. So it should be greater than equals k, okay? So when you use this probability, you use Poisson distribution. But if you want to use this probability, you're going to use Erlang distribution. However, for you to compute Erlang distribution, you should have the gamma table. But usually gamma table is not handy. That's why most of cases, if you are required to compute certain value, probability value using the Erlang distribution, then usually we go through Poisson distribution, okay? And then here's how you can do that, okay? So this is very important. Keep in mind that here T sub k follows Erlang distribution, but N sub t follows Poisson distribution, okay? And for the next one or two lectures, I'm going to give you a lot of different examples. And then we're going to come back out of this screen, okay? And then use these features later. So don't worry too much at the moment. And this screen just tells you the mean value and variance for the Erlang distribution, okay? So, and this screen also shows you the graph of the Erlang distribution. So as can be seen here, as k value increases, the distribution becomes less skewed, right? And more becomes normal. Is that right? So in the limit, as k goes to plus infinite, then k Erlang distribution converges to normal distribution. Okay, that is nice feature. Okay. Okay, now I'm going to summarize what you've learned today. In a Bernoulli process, each random variable is independent of each other. And what else? Each random variable follows Bernoulli distribution. Is that right? So keep in mind that. That's very important. Okay? And suppose there is a probability of P of being a success on any single trial, right? And then if we make n independent trials, then the binomial random variable counts random number of successes within that n different trial. Is that right? If you make that independent trial over and over, then the geometric random variable counts the number of trials required until the first success. Is that right? And then negative binomial or Pascal random variable is the generalization of the geometric random variable, right? So it counts the total number of trials required to obtain the kth success. Is that clear? Okay. Next, we also talked about Poisson process, right? Poisson process is a special type of counting process. And then it satisfies two different conditions. What is that? Stationary increment, and then what is that? What? independent increment, okay? And the Poisson random variable is a count of the number of events that occurs during the given time period, is that right? And the time between arrival follows exponential distribution. Also, the exponential distribution measures the time required, time needed for the first arrival, okay? So I put the exponential distribution right here, okay? So keep in mind that both time between arrival, time needed for the first arrival. And k-Elang distribution measures the time needed for the kth occurrence, right? So that corresponds to this, okay? So I want to add more comments on this. Nice picture here. I'd say the easiest way to distinguish between the Bernoulli process and Poisson process is what? No. I'd say the parameter P. Okay? When you consider the Bernoulli process, you always deal with parameter P. What is the parameter P? Probability of being a success. What is that? Why is that? Because you remember, Bernoulli process, in the Bernoulli process, each random variable follows Bernoulli distribution. Okay? What is the Bernoulli distribution? Okay? To consider the Bernoulli distribution, we need to consider Bernoulli trial. Is that right? Bernoulli trial always has either of two outcomes, either success or failure, with certain probability P of being a success. So when you consider the Bernoulli process, you always consider the probability of being a success. Okay? So Bernoulli process always deal with probability P. However, when you consider the Poisson process, instead of considering P, you need to deal with lambda. What is lambda? That is the average rate. I'd say is arrival rate. Okay?
One divided mean.
Yeah, mean time. Right. If mean time is given, then you need to come up with mean rate. Usually take the reciprocal of that, right? So just keep in mind that when you consider the Poisson process, you always deal with lambda. So that is the key difference between the Bernoulli process and Poisson process. Okay? Keep in mind that. So I really like this picture. Okay? So that at least you know how to distinguish among those 6 different distributions. Okay? So next class, we're going to use this picture, okay, while we are solving many different example problems, okay? So this is all for today, and I'm going to meet all of you next Tuesday, all right, same time. And also don't worry if you miss the class, because the recorded lecture will be posted on our distance server, probably within 1 or 2 days. Okay? Okay.
Can we access those through the
Yeah. I provide a link, direct link, within the class homepage, so you should be able to do that. Okay? Yeah. Thank you very much for everyone. See you next time. Bye-bye.